Welcome to qnawire.
For problem 131, we're asked to find the centroid of a hemisphere that is cut in half, and it's a hollow hemisphere, also known as a hemispherical shell. And to do that, we'll use the equation where the centroid times the volume is equal to the integral of the centroid of a differential element. And the differential element of this hemisphere is going to be a thin slice in the xy plane that's integrated across the hemisphere, where that slice is going to look like this. And we can also, starting off, we can note that the centroid in the x direction is equal to 0 because of symmetry. Now for this differential element here, we can say that the radius, I'll call capital R, of the hemisphere, and the thickness of this slice is going to be that radius d theta, where theta is the angle to the center point of that slice. And then the radius of our slice, I'll call little r, and we can find that the differential area is equal to pi r, or the circumference, or a half circumference, times its thickness, which is capital R d theta. And we need this to find the volume, because the volume is equal to the integral of the differential volume or rather, since it's a thin hemisphere shell, it'd actually be the area that we're using in this problem. And so we need dA, the differential area, to solve for the total area for our equation of the centroid. And we also know from that slice that our centroid of the differential element is going to be equal to -2 times the radius over pi, which is the centroid of a half circle, when it's just a like a wire, not the entire area, just a line, a half circle line or arc. And now we have to solve this problem in terms of the radius of the hemisphere, not the radius of the slice. So to get this radius of the slice in terms of the larger radius, it's just going to be the larger radius times the sine of that angle theta, which means that we can now plug in that for our differential element. You get -2 times the large radius over pi sine theta. So now let's solve for the area, which we'll need to find the centroid. We're going to integrate from 0 to pi over 2, or a quarter of a circle, because that is the entire quarter hemisphere we're looking at. And then we can plug in the dA we found. And also plug in terms of the capital R for the radius of the hemisphere. So it's pi r squared sine theta d theta. And solving the integral, we get that it's equal to pi capital R squared negative cosine of theta from 0 to pi over 2, making our area equal to pi capital R squared. Now we need the right side of our centroid equation, which is the integral of the centroid of the differential element. So we can plug in the centroid of the differential element we found, and then multiply it by the our dA. That was this, it'll be the same one, differential area of that slice. Solving the integral, we get -2r cubed theta over 2 minus sine of 2 theta over 4 from 0 to pi over 2. And plugging in the 0 to pi over 2, we get that the integral of the centroid of the differential element is equal to -pi over 2 r cubed. And now we know everything we need to solve for the centroid using our equation. So we have the area we solve for. And then we can plug in the centroid, the integral of the centroid of the differential element we just found. And now solving for the centroid in the y direction, we get that's going to be equal to -1/2 times the radius of the hemisphere. Now since this is a hemisphere, it's symmetrical in the y and z direction for their